Welcome to everybody. It is my pleasure to start the last joint IFAC IEEE Control System Society webinar series on nonlinear controlled systems. This seminar will be given by Toshiyuki Ohtsuka, and I will co-chair this seminar with Hiroshi. So thank you very much, Hiroshi, also to be here. Thank you to Toshiyuki to participating to this series. So a few words before we start on the on Toshiyuki. He has attended the Tokyo Metropolitan Institute of Technology, where he has taken his bachelor degree and master and doctoral PhD. Then he has attended the Tsukuba University, where he was assistant professor. Then he moved to Osaka, where he as a professor, and finally he joined Kyoto University as a professor at the Graduate School of Informatics. His research interests concern real-time optimization algorithms and with application in particular to mechanical engineering, and this actually will be the focus of this talk, as I understand. And he is author of more than 200 publications in systems and control. He's a recipient of many prizes from the SICE, so the Outstanding Paper Award in 2004 and 2013, the Book Award in 2012, and the Control Division Pioneer Award in 2006, and Kimura Award in 2014. He is actually a member of SICE and a senior member of the IEEE and the AIA societies. So thank you very much for being here. And now I leave you the floor for your talk. Thank you.
Okay. Yeah, thank you very much for introduction, Claudia. Okay, hello everyone, and let me share the screen now. Okay, so I guess you can see my screen. Okay, hello everyone. I'm Toshiyuki Ohtsuka from Kyoto University, Japan, and it's my great honor to give a talk in this webinar series. So today, I'm going to talk about real-time optimization algorithms for nonlinear model predictive control of non-smooth dynamical systems. This talk is based on joint work with my PhD students, Sotaro Katayama and Kanju Lin. The topic of this talk is numerical computation and would be different from those of past talks in this webinar series, but I hope you will enjoy. Okay, and this is the outline of my talk. I guess most of you already know the idea of MPC, but just to be sure, I will give you a very brief overview of MPC first. Then I will talk about fast MPC of robotic systems with rigid contacts, which is a special but important class of non-smooth dynamical systems. The point here will be that we deal with the whole body model of a robot without simplification. And we optimize not only a trajectory, but also switching times due to contact of the robot with the environment. Here we assume that contact patterns, placement of contact are given beforehand, but this is obviously a computationally demanding and challenging problem because the whole body model of a robot with rigid contact is extremely complicated. Actually, it is even impossible to write down the equations of motion explicitly. However, we will introduce some numerical computation techniques for efficient optimization. And finally, I will show you that real-time optimization is in fact possible in a hardware experiment of a quadrupedal robot. After that, I will also briefly introduce a numerical solution method for even more difficult problems, that is, optimal control problems with equilibrium constraints. This is a very general framework for optimal control of non-smooth dynamical systems. For example, in the case of a robot, we optimize not only the trajectory and switching times, but also the contact pattern. This is, of course, even more challenging than optimization of switching times for a given contact pattern. But we are now working on a promising method for numerical solution. Okay, let us now begin with a very quick overview of MPC. As you may already know, MPC is a kind of feedback control by real-time optimization of a system's response over a finite future at each time instant. So let's see. Oh, yes. Yeah, if you have any questions, yeah, please free to ask anytime you want. Okay, let me continue. So yeah, so as you already know, MPC is a kind of feedback control by real-time optimization of a system's response over a finite future at each time instant. And it is a very general and useful approach to control complex systems as long as real-time optimization is possible. I guess you know some eye-catching applications of MPC in recent years, including a landing rocket, a humanoid robot, and autonomous drifting car. Since MPC can be viewed as a general framework of real-time decision-making for various intelligent behaviors, so MPC also attracts growing interest of the machine learning community in recent years. For example, there was a tutorial on MPC in a top conference on machine learning, and there is a big EU project exploring interdisciplinary areas of MPC and machine learning. And in our systems and control community, MPC is regarded as a powerful approach to nonlinear control. And in recent years, MPC also attracts growing interest of the robotics community. So there are various challenges and opportunities in MPC. So what is MPC? As I mentioned, MPC is a kind of feedback control by real-time optimization of the system response over a finite future at each time instant. For example, let us imagine we are driving a car on a dark night road where we can see objects only in the range of the headlight. Then we should predict the motion of the car and optimize our driving action over a foreseeable future based on available information for safe driving. So we have an optimal control over a finite future in our mind, but we use only the initial value of the optimal control corresponding to the current time in the real world. It is meaningless to use the optimal control at any other time instance in the future because we are at time t in the real world. Then after a moment, our car proceeds and we get new information. Then, of course, we should update our prediction and optimal control immediately based on new information, right? An important point here is that we update our control action within a much shorter time interval than the horizon of prediction and optimization. I don't think you drive a car without updating your optimal control action for, say, 10 seconds, or just because you have optimized your action for 10 seconds in the future. I guess you update your action every 1 second or less, I don't know, but by taking new information into account. Then doing these things at every time instant, we can drive the car safely, avoiding obstacles. This is the idea of MPC. So yeah, so MPC. So I think most of us, the idea of MPC is very natural, and most of us are doing similar things in our daily lives to make some intelligent behaviors. So MPC is a very general framework of feedback control of nonlinear dynamical systems because it can determine a reasonable control action, as long as the future response of the system can be predicted and optimized in real time. And the most important feature of MPC is that it has a receding horizon, as shown here. So suppose we are at time t in the real world, then we predict and optimize the system response over a finite future from current time t to t plus capital T. However, we use only the initial value of the optimal control as the actual input to the system. Then after a moment, the horizon moves toward the future and we re-optimize the control input over the shifted horizon. And again, we use only the initial value of the optimal control as the actual input to the system. And we discard the rest of optimal control input over the horizon. So it may sound wasteful to compute future input that are not used in the actual system, but the future input is necessary to predict the future response so that we can determine the best input at the current time. And by introducing the idea of the receding horizon, MPC can be easily understood as a variant of finite horizon optimal control problems. The future response of the system can be predicted by using the state equation, and constraints are also considered in general. We consider nonlinear systems in general, and then MPC is called nonlinear model predictive control, NMPC. Then at each time t, the control input of a finite future is determined to minimize a given performance index from current time t to t plus capital T. So the only difference of MPC from a standard optimal control problem is that the horizon of this performance index is not fixed and moves as time increases. And if the optimal control you opt, minimizing the performance index, is obtained, then, as I explained, only the initial value of the optimal control is used as the actual input, U of t, to the system. Please note that this. Please note that the initial state in the optimal control problem is given by the current state x of t of the system, because the initial time of the performance index is current time t. And of course, this optimal control depends on the current state x of t. So the actual input to the system implicitly depends on the current state x of t, and MPC is a kind of state feedback. And remember that we cannot find this state feedback explicitly as a function of x and t in general. Instead, we can just compute the input numerically, and the numerical solution depends on the current state. Now, let me briefly summarize the history of MPC. Similar ideas as MPC go back to 1950s and 1960s. They didn't use the word MPC, but they proposed control methods based on real-time optimization over a finite future at each time instant. Then in 1970s, some people have pointed out that stabilizing state feedback gain can be found by solving a finite horizon linear quadratic control problem, which can be viewed as a kind of MPC. Meanwhile, some MPC-type control methods have been proposed in the field of process control with different names: predictive functional control, PFC, dynamic matrix control, DMC, quadratic DMC, and generalized predictive control, GPC. They are basically formulated for discrete time linear input-output models. And from 1980s to 1990s, some people have shown the closed-loop stability of nonlinear MPC based on state space representations. their theoretical results and practical implementation of NMPC was not realistic at that time. Finally, since 1990s, some people have started to work on numerical solution methods for MPC. The mainstream was offline computation of optimal solutions to construct the state feedback as a function of the state explicitly beforehand, which is called explicit MPC. Essential drawback of explicit MPC is that it suffers from the curse of dimensionality and applicable only to low-dimensional and simple systems. However, at the same time, a few people, including myself, have also started to develop real-time optimization methods for nonlinear MPC, which will be the main topic of this talk. And now in recent years, application ranges of MPC has been expanding from chemical processes to fast mechanical systems, including automobiles, rockets, and humanoid robots. Okay, now let us start part one, fast MPC of robotic systems with rigid contact. Basically, there are two reasons to apply MPC to robotic systems. First, MPC can treat general nonlinear systems, tasks, and constraints in a unified manner. Second, the future prediction and planning in MPC are particularly important for some sort of dynamic control in robots. For example, these jumping robots must predict and plan their landing before the liftoff. Otherwise, they cannot determine appropriate places and timing for touchdown and may fall down. Moreover, the prediction and planning of these jumps need to be updated online to compensate prediction errors due to sensor noises, modeling errors, unknown disturbances, and so on. So MPC is a natural and universal strategy for controlling complicated robotic systems. However, there are several challenges in real-time implementation of MPC for robotic systems. First, the computation time of MPC is limited to a millisecond range, typically from 1 millisecond to 10 milliseconds, because fast robot dynamics require high control frequency, a short sampling period. Second, we have to solve high-dimensional and highly nonlinear optimization problems within such a short sampling period. For example, a typical quadrupedal robot has a 36-dimensional state, 12-dimensional control input, and a very complicated nonlinear state equation with constraints on joint angles, joint torques, and friction forces. Third, a robotic system has such as a quadrupedal robot involves non-smooth dynamics and state jumps due to contacts with the environment. Robotic systems with contacts are formally modeled as hybrid systems, and MPC of hybrid systems is known as a very difficult problem because of discontinuities and switches in the dynamics. And so because of these difficulties, existing robotic applications of MPC are limited to some sort of approximated formulations at the expense of optimality. And now let me briefly summarize existing approaches to MPC of robotic systems. First, the dynamics of a robot are often approximated by a simplified model, such as single rigid body dynamics. However, there is a strong assumption that we can control each joint velocity and contact forces arbitrarily. Another common assumption is that each limb is negligibly light and its kinematics can be disregarded. Second, approximations are also introduced in optimization problems. For example, single rigid body dynamics are often further linearized to simplify optimization, and contact timings are also fixed in almost all of the existing methods. So, although existing MPC sometimes works well, their performances depend on hardware platforms, tasks, and other specific settings. So they are not general enough. So our goal is to develop general and practical algorithms for MPC of various robotic systems with contacts. In particular, we would like to develop algorithms to realize real-time optimization for MPC, even if we use exact whole body dynamics and rigid contact model, which we call whole body MPC. Moreover, we would also like to optimize the contact timings of the robot with the environment, as well as the trajectory for better performance. To achieve our goal, there are some technical challenges listed here, and we propose some new techniques to solve these problems, which are our contributions. But today, we will focus on the last two topics in part one due to the limitation of time. I mean, efficient optimization of switching times, as well as trajectory and also integration to whole body MPC. Then I will show you that whole body MPC of a quadrupedal robot is possible in a hardware experiment. And now, okay, before getting into technical details, let me briefly introduce two paradigms in formulation of MPC or optimal control for robotic systems with contacts. One is so-called contact implicit approach, where we try to optimize everything without any pre-specified references. For example, in the case of a walking robot, we have to optimize the contact pattern. I mean, when and where to place which leg on the ground. So we have to optimize the contact pattern as well as trajectory, which leads to an optimization problem involving binary variables or complementarity constraints. Then this kind of optimization problem is very hard to solve, even in offline, due to the combinatorial nature of the problem. Another formulation is called contact explicit approach, where we assume that a higher level planner gives contact patterns about placement of the legs beforehand. So for a given contact pattern, MPC just optimizes the contact timings or switching times and the state and control trajectories. In this case, we don't have to care about combinatorial optimization. So this approach would be more practical than the contact implicit approach. However, we still have to deal with discontinuities in the dynamics and also have to optimize the switching times. So it is still challenging to implement MPC based on the contact explicit approach. And basically the contact explicit approach will be the topic of part one in this talk, but I will also introduce our ongoing work on the contact implicit approach later in part two. Okay, now I briefly explain the model of robot dynamics. Of course, dynamics of a robot are very complicated, but after all, we can derive a state space representation as shown here. The state vector X consists of the configuration Q and the generalized velocity V. And the configuration Q consists of joint angles, the position and attitude of the robot. The control input U consists of joint torques. Then we have a state equation to describe continuous dynamics and a state jump equation to describe discontinuous jumps of the state at contact. The important point here is that the structures of these state equation and the state jump equation switches depending on the contact mode of the robot. That is the combination of legs on the ground. So this is a complicated hybrid system, and its optimal control is, of course, a difficult problem. There are also some inequality constraints to be satisfied at every time instant. For example, the position, velocity, and torque in each joint are in general limited within certain ranges, and moreover, friction forces between the legs and the environment are also limited, which are often represented as friction cones. As I mentioned earlier, we assume that the contact pattern is given about placement of the legs by a higher level planner. Then at every sampling time, we optimize the control input and switching times by minimizing a performance index over a finite future, subject to the state equation, state jump equation, equality constraint, describing the contact, and inequality constraint representing limitations in some variables. And this is nothing but an optimal control problem of a switched system with switching time optimization. Of course, there are some existing approaches to optimal control problems with switching time optimization. One of conventional approaches is a so-called two-stage method, which divides the optimization problem into two parts. Optimization of switching times and optimization of the trajectory, and solves these two sub-problems alternately. But in general, this approach suffers from slow convergence, and it is difficult to guarantee local convergence. Another approach is simultaneous optimization of the switching times and the trajectory. This approach would be natural, but in general, it is conditioned or computationally demanding due to discontinuities in the problem. So this has not been suitable for MPC of fast and large-scale robotic systems. However, in our approach, we developed an efficient computation method for the second approach, the simultaneous approach, to optimize the switching times and trajectory simultaneously. A key idea is efficient computation of a Newton step by a generalized form of the Riccati type recursion. And moreover, we also introduce fast reduced Hessian modification to ensure numerical robustness. By introducing these techniques, we can realize simultaneous optimization of switching times and trajectory efficiently. Okay, and to solve this optimal control problem numerically, we first discretize this problem into a finite dimensional optimization problem by the direct multiple shooting method. That is, we introduce a finite number of discretization grids and introduce the state and control input on each grid. Then the optimal control problem is reduced to a nonlinear programming problem. In particular, we basically fix the number of grids between the switching times and apply an interior point method with a fixed barrier parameter. Then we can guarantee the local convergence of a Newton type method because we are simply solving a nonlinear programming problem of a fixed structure. Moreover, if the discretization step exceeds some threshold during iterations of the Newton type method, we perform the mesh refinement to adjust the discretization step to keep the accuracy of numerical computation. If the threshold for the mesh refinement is sufficiently small, we can expect the mesh refinement does not affect the solution and local convergence. Okay, or let's see, are there any questions now? Okay. Sorry. What would be a typical horizon for typical application? A few fractions of second, and if not, system is operating virtually in open loop mode. In a sense that would be similar to sample data control with large sampling period. So typical horizon would be, let's see, a couple of seconds or just around 1 second. But our sampling period is actually in the order of milliseconds. So that's very important. So yeah, that's the essential feature of MPC, right? Control input is updated more frequently compared to the length of the horizon. Okay, did I answer the question? And yeah, I will show you that, in fact, real-time optimization for the whole body MPC is possible later. Okay. Okay, then furthermore, we would like to perform the Newton type method efficiently. So as I mentioned, so in a millisecond range of computation time. But so like this. But the problems here are how to achieve fast computation and how to ensure numerical robustness in the computation of the Newton step. And please note that we cannot use general QP solvers that assume the positive definiteness of the Hessian matrix, because the Hessian matrix in this problem is inherently indefinite because of switching time optimization. So we propose a recurrent recursion algorithm tailored for the present problem involving switching time optimization. It is very efficient, requiring the linear complexity with respect to the number of grids over the horizon, and it requires only the positive definiteness of the reduced Hessian matrix, taking the switching time optimization into account instead of the original Hessian matrix. First, we can show that the Newton type iteration is nothing but solving the following quadratic programming problem, a QP problem, where delta xi, delta ui, and delta tk denote the Newton steps of the state input and switching time, respectively. Please note that the index of delta t is different from those of delta x and delta u, because switches do not necessarily occur at every grid. And this quadratic cost function with the indefinite Hessian matrix is minimized with respect to delta ui and delta tk. And then delta xi is determined from delta ui and delta tk by this linearized state equation. Then we can derive a recurrent recursion algorithm by applying the idea of dynamic programming to this QP. That is, we can construct a sequence of smaller QP subproblems backward recursively, and then we solve this QP to determine each of delta xi, delta ui, and delta tk, respectively. This is efficient because we have to solve only a sequence of small QP subproblems. First, let us consider dynamic programming at the grid between switching times tk-1 and tk to determine the Newton step of the input delta ui. If we assume the cost to go can be represented in this form at stage i+1 between switching times tk-1 and tk, then we can find delta ui by minimizing this cost. And then we can show that the cost to go at stage I is also represented in the same form. So which means we can derive a recursive formula for these matrices and vectors in this small QP backward on the horizon. Next, we consider dynamic programming for the Newton step of switching time. That is, this cost to go is minimized with respect to the Newton step of the switching time, delta tk. Then we can show that the cost to go takes the same form even across the switching time, but by modifying the recursive formula for this matrix and vector. So after all, we can construct these matrices and vectors in QP recursively backward over the entire horizon, and then we can compute the Newton steps recursively forward over the horizon just by solving these small QP subproblems, which can be seen as a generalized form of recurrent recursion. So the computational complexity grows only linearly with respect to the number of discretization grids on the horizon. And this computation is always successful if the Hessian matrix of each each QP subproblem, this matrix is positive definite, which corresponds to the positive definiteness of the reduced Hessian matrix of the entire problem, taking switching time optimization into account. However, in practice, we cannot necessarily guarantee the positive definiteness of the reduced Hessian matrix if the iterate is far from a local minimum, which means that the Newton step is not necessarily a descent direction, or the Riccati recursion may fail. And existing methods cope with this problem by complicated operations, which requires a large computation cost. However, in our particular case of switching time optimization, we can introduce a very simple and fast modification of the reduced Hessian matrix, which I will explain in the next slide. Here we assume very mild conditions, which are normally satisfied by the Gauss-Newton approximation, and we simply modify these entries in this matrix in the QP subproblem to be positive semi-definite. Then we can guarantee this matrix is positive definite and the Riccati recursion works, even if the iterate is far from a local minimum. In fact, it is a very simple operation to just omit some operations in constructing these entries, like subtractions, which may make these matrices indefinite. So actually, it needs almost no computation cost. Okay, now let me show you a result of numerical comparison in this nonlinear switched system consisting of 3 modes. This table shows the computation times of the proposed method, general purpose solver, IP-opt, and SQP with general QP solver. General QP solver does not work in this particular problem due to the indefinite Hessian matrix, and the proposed method is 100 times faster than the general purpose solver, thanks to the tailored Hessian modification and Riccati recursion. Next, let me show you a numerical example of more complicated trajectory optimization. This is a trajectory optimization problem of a jumping quadrupedal robot with friction cone constraints and 2 switches when the robot jumps and touches down. Please note that this is not MPC, but offline trajectory optimization over rather long horizon. I mean, in this case, the horizon is, I guess, around 1.5 seconds. And this figure shows the history of switching times during iterations. We can see that they converge to local optimal solutions, and the mesh refinement is performed twice. This figure shows that the logarithmic value of the KKT residual decreases during iterations when the grid structure is fixed. The total computation time was 270 milliseconds, so this complicated problem can be solved quite fast. Okay, then now we integrate the proposed method to whole body MPC of a robotic system. As I mentioned earlier, in the existing approaches, some sort of approximation or simplification is necessary to reduce the computation burden of MPC for robotic systems. For example, some of existing approaches approximate the robot dynamics with a single rigid body dynamics, or they also simplify the optimization problem by fixing the contact timings in a heuristic manner. In contrast, in our approach, we deal with whole body robot dynamics, rigid contact model, and switching time optimization. Of course, it is computationally demanding and quite challenging. However, we succeeded to realize this challenging optimization in real time by the following techniques, including the fast Riccati recursion for switching time optimization I have just explained. But the first and second techniques are omitted in this talk, but I emphasize all these techniques are essential to realize real-time whole body MPC. Okay, next, we verify the effectiveness of the proposed MPC through physical simulations. Here we compare the proposed whole body MPC with online switching time optimization and the whole body MPC with fixed switching times. For both MPC, we gave the same initial guess, including the switching times. Then only the proposed method with switching time optimization succeeds in jumping simulation, which demonstrates the importance of switching time optimization. And we run both MPC at 400 Hz, which corresponds to a sampling period of 2.5 milliseconds. And the proposed method achieved 1.3 milliseconds computation time per update. That is, our method achieved real-time optimization, even with this complicated problem. Moreover, we have conducted a hardware experiment on a quadrupedal robot, Unitary A1, which has many actuators and sensors. Please note that some of the state variables cannot be measured directly, and we need to estimate them. In particular, we cannot measure the position, attitude, and velocity of the body of the robot. So we estimate these variables in the experiment. And this is a video of the hardware experiment. Oh, I'm sorry, the video is not so smooth on the Zoom. And as shown here, our MPC achieved successive dynamic jumping. The computational settings were the same as the numerical simulations, and that is, we run this MPC at 400 Hz, and the average computation time of our MPC was just 1.3 milliseconds, about a half of the sampling period. So we can implement MPC for the whole body dynamics of this complicated robotic system with reached contacts in real time. And let me also briefly introduce an open source software for MPC of robotic systems, Robotalk, which is available on GitHub. This is a rather specialized tool for robotic systems than a general purpose tool. In addition to the techniques I presented so far, an important component for MPC of robotic systems is a library of fast rigid body dynamics algorithms, Pinocchio. This is a very efficient library to compute forward dynamics, inverse dynamics, and their sensitivities, exploiting special structures in the dynamics of robotic systems. And if you describe the model of a robot in the so-called Unified Robot Description Format, URDF, then Robotalk defines a fast solver for MPC of the robot with simplified specified contact patterns. For example, you can easily perform numerical simulations of legged robots like these animations. Okay, now let me also introduce a numerical solution method for optimal control problems with equilibrium constraints. This is a very general framework for optimal control of non-smooth dynamical systems and can be applied to contact implicit models of robotic systems with contacts with no pre-specified contact pattern. I mean, we can optimize the mode sequence as well as the trajectory and switching times of a hybrid system. So, and this is of course even more challenging than optimization of switching times for a given mode sequence, but we are now working on a promising method for numerical solution. Okay, in general, an optimal control problem with equilibrium constraints is formulated as shown here. It looks like a standard optimal control problem consisting of the performance index, inequality and equality constraints, and the state equation of the system to be controlled. The only difference is the last constraints, which are called equilibrium constraints, defined by variational inequalities. I will show you in the next slide. Various kinds of switching phenomena such as contacts, frictions, and general complementarity conditions can be formulated in this form. Please note that there is no switching times explicitly in this problem. And that is the reason why this problem can deal with contact implicit models of robotic systems. Specifically, this condition is defined like this. This SOL operator gives the solution set of the following equilibrium problem. Find P in a given set capital X, such that this variational inequality is satisfied for all Y in the set capital X. So this is too abstract, and you may wonder what this condition means. So now let us focus on box-constrained variational inequalities without loss of generality, where set capital X is given by component-wise intervals. General variational inequalities can be transformed into this form, and then the solution set of each component of P and K is given by these line segments in this figure. And this set is expressed like these conditions. So you can imagine this solution set can represent various switching phenomena, such as contact forces and friction forces. Furthermore, these variational inequalities are also equivalent to a set of inequality constraints which violate standard constraint qualifications. I mean, a kind of ill-conditioned constraints can also be represented by variational inequalities. So variational inequalities can represent a very general class of problems. However, since variational inequalities are ill-conditioned constraints not satisfying standard constraint qualifications, so we modify them by introducing a small parameter S for numerical computation. The first method is a smooth approximation of a projection operator in an equivalent representation of the variational inequalities. Then the solution set is now modified to be a smooth curve like this dashed line in this figure. And the second method is the regularization of the inequalities with a small parameter S, so that the variational inequalities lead to a feasible region with interior points, like this green region in this figure. Then anyway, we can apply some numerical solution methods to the modified problem, satisfying constraint qualifications. Okay, now let us go back to the optimal control problem. So now these equilibrium constraints are reformulated as I explained in the last slide, where S is a small parameter. And if S goes to 0, this equality is identical to the original constraints. Furthermore, the horizon is discretized into a finite number of grids, and the state equation reduces to equality constraints. Then the discretized problem is nothing but a nonlinear programming problem, and its KKT conditions can be obtained like this. The first conditions are complementarity conditions, and they are also a kind of equilibrium constraints. So we introduce a smoothing approximation to these complementarity conditions again. In particular, we employ the so-called Fisher-Burmeister function with another small parameter z. After all, now we have a set of nonlinear equations for the state, input, costate, and other Lagrange multipliers over the discretized horizon. And thanks to the two reformulations we have introduced, we can simply apply Newton's method to these equations as long as S and Z are positive. And please note that Newton's method in the present formulation does not enforce the iterates to remain in the interior of the feasible region. So we call this method as a non-interior point method. And we can expect that this non-interior point method has a better convergence property than an interior point method because it can choose a large Newton step outside the very small and distorted feasible region. Furthermore, we can also apply the continuation method to gradually decrease the parameters S and Z towards 0 to improve the accuracy of the solution, avoiding numerical difficulties. Now, let me show you numerical examples. The first example is a linear equilibrium system shown here. This looks simple, but please note that the mode switching sequence is not given beforehand at all. However, the proposed non-interior point method generates a local optimal solution in this figure, and you can see a switching behavior generated automatically by the proposed method. And this slide compares the number of iterations between the proposed non-interior point method and a standard interior point method. In this case, we don't use the continuation method and S is fixed. You can see that the number of iterations of the non-interior point method does not increase significantly even for small values of the smoothing parameter S. You can also see that the non-interior point method outperforms the interior point method for small values of S. Okay, next, let me show you a more practical example, a three-cut system. Here, we would like to move these three boxes by actuating only the green box in the middle. So other two boxes, red and blue ones in the left and right, are just pushed by the green one. Of course, we have no predefined sequence when and which one we should push. However, the proposed method generates an optimal control input involving reaction forces, as shown in this animation. Okay, now I'd like to conclude my presentation. Our goal in part one of this talk was a real-time optimization algorithm tailored for MPC of robotic systems with rigid contacts. And in part two, we have also discussed a numerical solution method for a very general class of optimal control problems involving equilibrium constraint, which can formulate various problems with contacts, frictions, and switches without any predefined mode sequences. Then, in part one, we have realized the challenging online optimization for MPC of robotic systems by introducing several numerical techniques, including these I omitted today. I have focused on the first Riccati recursion tailored for optimal control problems of switched systems. Then we have achieved real-time MPC of a jumping quadrupedal robot based on the whole body model and rigid contact in both numerical simulation and hardware experiment. The computation time per update was just around 1 millisecond for optimization of whole body motion and switching times. Moreover, we have also developed a software tool for MPC of robotic systems, Robotalk, which is available on GitHub. In part two, I have briefly introduced a general framework of optimal control problems with equilibrium constraints and introduced some numerical techniques to solve them. Then we have demonstrated that the non-interior point method can generate optimal solutions with fewer numbers of iterations than interior point method, because the non-interior point method can choose a large Newton step outside the very narrow and distorted feasible region of the equilibrium constraints. And as the future work, we will apply our method to more variety of robotic systems and apply the non-interior point method to MPC of systems with equilibrium constraints. And these are some of our papers on the topics in this talk. And before finishing my talk, please let me make two announcements. One is the special issue on MPC for autonomous vehicle systems, which will be published in IET Control Theory and Applications. The deadline of submission is December 31st, 2023, and the special issue will appear in August 2024. Please check the journal website for details. And the other is the next IFAC conference on nonlinear model predictive control, NMPC, held in 2024 in Kyoto, Japan. This is one of the important conferences for the MPC community. The submission deadline is close to that of the special issue in the last slide, but topics of this conference is more general than the special issue, and I hope you can submit your papers to both. And I am serving as the chair of the National Organizing Committee and preparing for the conference with great help of Moritz Dill, serving as the chair of the International Program Committee. We will do our best to make this conference exciting and fruitful. As you may know, Kyoto is a historic city of Japan as an ancient capital for more than 1,000 years, and you can enjoy many interesting places and various interesting cultures. So please submit your papers and attend the conference. I'm really looking forward to seeing you in Kyoto. Okay, that's all. Thank you for your attention, and I'm happy to answer any questions.
Thank you. Thank you, Toshiyuki. I'd like to thank you very much, but although you are not able to see people giving a big hand. Yeah, but the presentation was really inspiring, and also you have good information of special issue and conference or symposium. We may be very interested in participate and submitting papers to. And I think we have time to have questions, and we'd like to have questions from audience. Do you have any questions? And you just, I think, start talking. If you have questions.
I am Eduardo Aranda from Mexico. I already asked something by the chat, so I'm sorry, I do not want to bother you. So may I?
Yes, you can now.
Okay, so I stick with the very same idea. There is this famous theorem by Shannon, which says that if you want to reconstruct some signal, you have to sample it fast enough. If not, you may see or you may think that a signal is constant, but it is not. It is just that you are sampling at a very low rate. So this is my concern with MPC. Can this kind of phenomena happen that you miss something because your horizon is too large and you miss the I know the transient of the system response?
So yeah, thank you, Eduardo, for asking a nice question. So I'm not sure if I really get your point, but in MPC, basically the sampling frequency is very high. I mean, sampling period is in the order of milliseconds. So basically, we don't miss any quick transient of the actual system, while the horizon is rather longer than the sampling period. So yeah, of course, there is a possibility that the performance is not good when we have modeling error or unknown disturbances. So because our control action is based on the prediction. So yes, we should predict as precisely as possible. But basically MPCs, but also still a kind of feedback control. So we can immediately respond to any unexpected disturbances or modeling, unknown, behavior of the system based on the very fast sampling of the actual state of the system. So yeah, so of course, there is a very how to say, active research is on robust MPC or stochastic MPC in our community. So did I answer your question?
Yes, thank you very much for your answer.
Thank you. Are there any other questions? Party, do you see any? Oh, yes, you can start.
Yes, thanks. Thanks, Ohtsuka sensei. I'm Ryozaki from Kyoto University, Matsuno Lab. Then I'd like to ask a question about MPC. And then my question is about the reference of in a model of MPC. It should be a constant, or it should be it also should be a change along the horizon.
Yes, of course. In general, the reference in MPC can be time varying. Yeah, of course. In general. Yeah, because
I mean, in the same horizon. In the same horizon, it should be difference. It should be changed.
Yeah, of course. So just we can take the time varying nature of the reference into account in our optimization. So yeah, it's in general possible, of course.
So what if we set like constant reference? Is it like a big problem, or it doesn't change at all?
Constant. So yeah, constant case is rather easier, right? But of course there may be some how to say, some issue in mismatch between the real system and the prediction.
Yeah, because the sampling time is kind of very short. So I was wondering if there's a big large error in the like even in a small sample time.
Yes. So I guess there may be some problem if the constant. So if while we assume a constant reference over the horizon, the reference input signal may change very quickly in the how to say next sampling time. Then there may be some problem in updating the optimal solution. Because if the reference changes significantly in a very short sampling time, then normally the optimal solution would also change significantly. Then it may take a rather long time to update the optimal solution. So maybe optimal, in the worst case, the optimization may fail within the sampling period. So of course, that's a possible problem.
I understand. Thank you very much.
Yeah, welcome.
Prof, do you see any questions in streaming or somewhere?
No, actually, we have around 30 people on streaming, but no questions.
Okay.
It's a method of, but there is a question.
Yes.
From Professor, is the method of OCPEC used within the proposed MPC algorithm, or is it for generating a reference trajectory for the MPC algorithm? Okay. So you mean OCPEC is a topic of the part 2 of my talk, and it's still under ongoing work, and we are working on only offline trajectory optimization. So it is not used in MPC algorithm, and of course not in the algorithm of part 1. So in the part 1, we assume the contact pattern is given beforehand. But in part 2, we also tried to optimize even the contact pattern. But it's still ongoing work, and the application to MPC will be the future work. Did I answer the question?
Okay. Any other questions? If not, I have a simple technical question because I'm not familiar with this area. I'm question is about the introduction of some 2 terms to make local Hessian definite.
Yeah.
And then I couldn't. Do you have any explanation of idea having only 2 terms there, and what kind of guarantee or what kind of things you can guarantee, or what kind of things you need to take care of when you introduce two terms?
Two term means.
Yeah, like to make Hessian, local Hessian.
Yes, yes.
You introduce something, but I'm not sure how much or how large modification are allowed, or how automatically the amount of the modification are introduced or guaranteed.
Yeah. Okay, thank you very much for very technical question. So basically, how to say? So yeah, so of course I omit the detail of the algorithm to construct these entries in the matrix. But basically we can see which term is positive semi-definite and the another is not. So, and of course we have some matrix subtracted in the update formula of the matrix. But so if we subtract some matrix, which is in general positive semi-definite, then it can make the resultant matrix indefinite. So if we want to make the updated matrix positive semi-definite, then we can just simply omit just some operation like subtracting some matrix. So then we can at least guarantee the positive definiteness of the Hessian matrix in the QP subproblem. So, but of course, it's a kind of approximation, but it makes really the computation robust, even if the solution is far from a local minimum.
Okay, you can make the computation robust at the cost of some discrepancy with respect to the optimality.
In some sense, yes. In some sense, yes.
Okay, there is a technique.
How to say? But anyway, once it converges, we can get the local optimal solution. But how to say? So basically, we are using Newton's method. So we need in the original form of Newton's method, we use the exact Hessian matrix of the problem. But in reality, Newton's method with exact Hessian does not necessarily perform well. If the solution is the estimate of the solution is far from the real solution, then it is common to introduce some
now I understand your idea. Yes. Thank you. Okay. Do you have any other questions?
Very, very, very last remark. And Newton method has also the problem of ill-possedness of the problem. When you have a very slow, a very, very small slope of the.
Yes.
You can go very far and come back and.
Yes, exactly. So that kind of situation could also be avoided by defining the Hessian matrix.
Sorry. I'm abusing of your time. Sorry.
No. Thank you.
Thank you for interesting question or comments. And is there any other questions? I think Claudia, I think we can close this seminar, right? Claudia, right?
Yes, I would like to thank again Professor Ohtsuka for the great, fantastic seminar that he has given, and I think that everybody who is not familiar with the model predictive control will have benefit of this talk. And I would just also remind that this should be the last seminar of the year, and we will start next year. The next seminar is supposed to be by Rodolphe Sepulcre, and time and date exactly will be announced on the website as always, and it will probably be on January. So just check for that. Okay, so thank you very much to everybody for attending the seminar, and thank you again to our speaker.
Thank you,
Thank you very
Toshiyuki.
much.
Thank you,
Thank you.
Claudia. Thank you, Hiroshi.
Yeah,
Thank
and
you,
please
Aaron.
submit your papers
Claudia.
to the
Thank you
special
for your
and
participation.
MPC conference. Bye-bye.
Thank you.
Thank you. Thank you, Claudia.
Uh,